In this video, I want to talk about electron configurations that are regular, and then also talk about ion electron configurations. So we've set forth a set of rules for figuring out electron configurations. If you follow the Aufbau principle, Pauli exclusion principle, and Hund's rule, you'll be able to create reasonable electron configurations and orbital diagrams. But because there's always a but, some of our transition metals are going to have what we call irregular electron configurations, which means it's not going to be the electron configuration you would predict based on the rules that we learned. And the trick to this is that some of the s orbitals only partially fill before the d orbitals, or they don't fill at all. And so for these elements right here, it was chromium, copper, silver, gold, molybdenum, ruthenium, and palladium. We have an expected electron configuration following the rules we established in the previous lecture. And these are now what we see experimentally. So the rules don't work all the time. They're a great way of kind of bookkeeping and predicting, but they're not always going to be the lowest possible energy for that atom and how it configures its electrons. But experimentally, we can see that lowest energy configuration. And so what happens in chromium, rather than it being 3d4 and 4s2, it becomes 3d5 and 4s1. And so the difference here is that the 4s orbital is half filled. And that 3d orbital is now half filled too. And what happens in as we're filling these up there, and this kind of explains Hund's rule, where you half fill all of your orbitals of the same energy first before you pair electrons, is that once you start pairing electrons in the same orbital, there is a greater amount of repulsion that will occur within it, and that actually destabilizes the orbital. It increases its energy a little bit. So there's actually a stabilizing effect of having the orbitals half filled. And when they're all half filled, it kind of lowers the energy a little bit. There's a stabilizing effect when they're all filled as well. And so whenever you completely fill a set of orbitals at the same energy, or you half fill them, we actually see a little drop in the energy. And so that little drop in the energy, especially when you get to the higher end levels, like above 3, then what we see is that little depression in energy actually brings the, let's draw it out. It brings that, so here's our 4s2, and here's our 3d. If this lowers a little bit, then it actually becomes more energetically favorable to half fill that 3D set of orbitals rather than have only 4 of the 5 filled with 1 electron. And so there will always be this effect on half filled and completely filled. And that's what we see in these expected versus experimental electron configurations. Like when you look at copper, copper should be 3d9 4s2, but one of those s electrons is promoted into the d orbital because that lowers the energy a little bit and makes it energetically favorable. So that way we have a filled d electrons and only 1 electron in the s orbital. And that ends up being a more stable configuration. So all of these exceptions, and I don't think they're worth memorizing necessarily, but it is worth knowing the reason behind them and what is going on in the structure of the atom. All right, now let's switch gears to ions. So ions with predictable ionic charges are listed here below in this page. And that's really just, it's not a lot. It's really the first 2 groups are always going to be +1 or +2. Any metals that aren't post-transition metals, so in group 3, so that's just aluminum, because above that boron is a metalloid, will be just +3. And then in groups 5, 6, and 7, we have some predictable charges as well. For nitrogen only out of group 5, but then groups 6 and 7 are predictably -2 and -1. So for these predictable ions, then we can create predictable electron configurations for the ion itself. And that's just adding additional electrons into the lowest possible energy level. And so when we do that, we'll see that it always ends up being the noble gas electron configuration, right? That's kind of the drive for the ion's formation. Oxygen gains 2 electrons because that gives it the same electron configuration as a noble gas, which is more stable than oxygen's electron configuration because all of the orbitals are filled. So anything that's an anion will have the same electron configuration of its nearest noble gas. And anything that's a cation will have the same electron configuration of the noble gas in the n level above it, because it will be losing electrons rather than gaining them. And so for something like strontium, which we've been looking at throughout this lecture, we can look at strontium plus 2. See, it's right here. And so it'll have 36 electrons instead of 38. And so it's going to lose those 5s2 electrons, right? And then what we have is just the electron configuration for krypton.